All right, hello. So following our last video and our discussion of property changes upon mixing and partial molar properties in ideal solutions, next I want to talk about fugacity in ideal solutions. Right, so in this set of notes, we'll talk about fugacities in ideal solutions, and then we'll have another one more set of derivations in which we talk about Rayoult's law before we put Rayoult's law into practice. So the key when I talk about fugacity in ideal solutions is in the last set of notes we found that our expression for the partial molar Gibbs free energy of component I in my ideal solution, right, took the form of G bar I ideal at Tp and Xi was equal to the pure component value at T and P plus RT log Xi. Okay, so this is the key. All right, now remember my partial molar Gibbs free energy of my ideal solution, right? That's equivalent to the chemical potential of component I in my ideal solution at given temperature, pressure, and composition. Okay. All right, so in terms of getting our expression for fugacity, we can work with either one of these expressions. I'm going to take this first one, okay, and I'm going to rewrite this. So I bring over my Gibbs free energy of my pure component system over to the left-hand side, G bar I ideal, okay, and that's at Tp and Xi minus Gi at T and P is equal to RT log Xi. So whenever I have a difference in molar Gibbs free energies at the same temperature, right, immediately I think of fugacity. Okay, so this is equivalent to, the left-hand side is equivalent to RT times log. So this would be the fugacity of component I in an ideal solution at Tp and Xi relative to Fi at T and P. Okay. And as a note, this is the fugacity of pure component I at T and P. So oftentimes we'll put a superscript pure on there just to remind ourselves. Okay. And then also, just like when we introduce residual properties, right? We're kind of thinking of this as a reference state. It's reminding ourselves we're taking this kind of reference state to be that of a pure component solution. And again, to bring it full circle in chapter 12, what's going to be key is all solutions approach ideal behavior in the pure component limit, right? A pure component solution is an ideal solution. Okay. But anyways, so for now I just put a superscript pure on there to remind myself that it's a pure component state, and that's equal to RT log Xi. Okay. So I can cancel RT, and if I were to take the exponential of both sides, I could end up finding, or I would get that the fugacity of component I in an ideal solution at Tp and Xi is equal to mole fraction Xi times the fugacity of component I, right, in my pure component state at T and P. Okay, cool. Okay. All right, and so before we move on, right? So we're going to talk about calculating this fugacity of my pure component state next, but the second half of the book, in this chapter, right, too, right, it's all about seeing similarities to what we've done so far. Okay, and so if I take a step back, right, or take a pause as we look at this expression, remember where we said where we're going with chapter 11 and then chapter 12, right? And so when we've discussed expanding our fugacity, so if I'm calculating the fugacity of, say, some component I in some mixture, Tp and Xi, so far what we've done is we've expanded with respect to an ideal gas reference state, right? So that took the form of log Phi at Tp and Xi plus the log fugacity of component I in some ideal gas state, right? And that'd be, say, at Tp and Xi. Okay. And so now the key has been, right? So I'm calculating my fugacity as being equal to some value at some reference state plus my deviation term. Okay. Cool. Now when it came to the fugacity of component I in my ideal gas, right, the fugacity of component I in an ideal gas at Tp and Xi, all right, that was just equal to partial pressure, right, mole fraction times P. Okay, so our fugacity was equal to this deviation term, and then our reference term, right, it's going to take the form of mole fraction times P. Okay, and so what's going to happen here is what we're going to get to in chapter 12 is when we're modeling liquids, an ideal gas reference state isn't going to be the best choice. Okay, so we're going to expand instead with respect to an ideal solution, right? So we're going to take my reference state or my idealized state to be that of an ideal solution. Okay. And so my fugacity is going to be that of my idealized state plus my deviation term gamma. All right, and again, just to show similarities, well, we just showed now the fugacity of component I in my ideal solution. Okay, that takes the form of mole fraction xi times Fi pure. Okay, so what we've done before is going to be very similar to what we're doing here, right? Our equations are going to look very similar. Okay, what we're trying to do though is we're just trying to take our reference state to be something closer to our state of interest. So modeling vapor phases, choosing an ideal gas as a reference state is great. When we model liquids, typically we take a reference state to be an ideal solution, right? So in an ideal solution, there are intermolecular interactions. We're just assuming that they're all different. Okay, and so this correction term, which we'll talk about in chapter 12, will account for the fact that my molecules are different sizes and my molecules interact in different ways. Okay, cool. Okay, so that's just my aside, right? Just to kind of remind you that there's going to be lots of similarities that pop up, right? And it's important to remind these similarities. Otherwise, it's too hard to remember everything, and it's important to see the connections to everything. Okay, so so fugacity of component I in an ideal solution is mole fraction times the fugacity of my pure component state, right? So kind of similar to what we had in the case of an ideal gas. Okay, so now coming back to this, so next I want to talk about calculating the fugacity of component I in this pure state, right? So I want to calculate this term. All right, and I'm going to write it in terms of log terms because our friend the pointing correction is going to come in, and so I want to make it so that we see our pointing correction, right, or remember what the heck the pointing correction is, and then we'll expand it out not in logs but in terms of actual terms. All right, so if I were to calculate the fugacity of component I in a pure component state at T and P, so we've done things like this before. Okay, so I'm going to write that the log fugacity of component I, okay, and remind myself this is a pure component state at a given temperature and pressure. Okay, well, I can write this as the log fugacity of component I at saturation at T, and then the pressure would of course be the saturation pressure. Right? Remember, this is a pure component state plus, and then put in brackets. So what I think of as my pointing correction is the log fugacity of component I at T and P minus the log fugacity of component I at saturation at T and P. Okay, cool. Now I want to look at each one of these terms individually. Okay, and I'm writing it as this just because it's easier to see or remember when we think about pointing. Okay, so the first term I want to look at is this one. Okay, so what's key is we're talking about the fugacity of pure component I, right? Pure component state. So this first term is the fugacity of component I at the same temperature but a pressure equal to my saturation pressure. So what this first term corresponds to is I have pure component I at vapor-liquid coexistence at that same temperature. Okay, so let's imagine I'm water at 100 bars, just because I can remember saturation pressure of water. Okay, so maybe this is the fugacity of pure water at 100 degrees C and 10 bars. Okay, this first term would correspond to the fugacity of pure water at 100 degrees C but 1 bar, right? The saturation pressure of water at 100 degrees C. Okay, so now what's going to be key is this first term. Okay, that corresponds to the fugacity of, say, pure component I at vapor-liquid coexistence. At vapor-liquid coexistence, the fugacity of the liquid and the vapor are equal to each other. Okay, so I could calculate the fugacity of component I in the liquid at saturation. I could calculate the fugacity of component I in the vapor at coexistence. They'd be equivalent to each other. Right? So I could use either one as a route to calculate the fugacity of component I at saturation. And so now actually looking back at my aside, we said it before, we would expand with respect to an ideal gas. When we model liquids, we're going to expand with respect to an ideal solution. So what I'm going to do here is, since this can be either liquid or the vapor phase at saturation, because they're both the same, I'm going to think in my head in terms of modeling the vapor phase at saturation. Okay? And in doing that, okay, or the reason for doing that is, remember, this is pure, right? This is pure component I. So there's going to be no mole fractions, right? It's pure component I. And the reason for doing that is, well, if I expand like we did before, excuse me, then the fugacity of component I at saturation would be equal to the fugacity coefficient of component I at saturation at T and P sat. Remember, this is a pure component state times just the pressure, where here the pressure would correspond to the saturation pressure. Okay, cool. So this first term, I'm just going to write as Fugacity coefficient at T and PSAT times P PSAT, right? And the reason we do this expansion is, well, if I find that I'm at low pressures, then it might be reasonable to assume that my Fugacity coefficient is just equal to 1, so that my Fugacity at saturation is just equal to PSAT. Okay, so it gives us this hierarchy with which we can make approximations. Okay, on the same token, I'm going to look at the second term. Right, the second term is our pointing correction. Right, and we can tackle the pointing correction in a couple different ways. Right, and we're usually going to kill it, so it's not going to make a huge difference. Okay, but in terms of my pointing correction, so here I have logs. So the first way I could write it is I would have to go back to my expression for dimensionless G. I'm holding temperature constant, so I integrate my pressure dependent term, and I would end up with that this would be the integral from PSAT to P V over RT dP. In order to integrate this expression, I would need to know how V changes with respect to P. So remember, the common case is that we assume that we're dealing with a compressed liquid, so that the molar volume can be assumed constant. And so when we have an incompressible fluid and volume's constant, V over RT, right, that's all constant, I could take it out. And this just becomes V over RT times P minus PSAT. Okay, and that's if I'm thinking in terms of logs. If I want to think in terms of F, it would be the exponential of this term. All right, so this is just my pointing correction, and the pointing correction just corresponds to essentially the Fugacity at some pressure of interest relative to the Fugacity at saturation. All right, so this is actually PSAT. Right, I put the sat up there relative to saturation at the same T. Okay, so putting it together then. Okay, so this is in terms of log Fugacity. This is just Fugacity. But if I put it together just in terms of F, okay, I'd have the Fugacity of component I in my pure component state at T and P is equal to the Fugacity coefficient of component I at saturation at T and the corresponding saturation pressure PSAT times PSAT times my pointing correction. Okay, and I'm going to put a functional dependence of T in here because my saturation pressure is, in theory, a function of T. Okay, times exponential of my pointing correction, which I'm going to write as V over RT times P minus PSAT. Okay, and again, part of the reason for expanding this is let's go through kind of what we've thought about so far in this class. Okay, so let's imagine I'm trying to calculate the Fugacity of, let's say it's water at 25 degrees C in 1 bar. I'm going to calculate the Fugacity of pure water at 25 degrees C in 1 bar. Right, and I say 1 bar, right, because if I think about my pointing correction, okay, we're at low pressures, right, and so we can assume that my pointing correction is going to be negligible. Right, so if I'm at low pressure, it's well removed from my critical point. Right, it's typically pretty reasonable to assume that my pointing correction is negligible. Right, so this term would just be, that would be 0, so the exponential of 0 would be 1. Okay, and when I say water at 25 degrees C in 1 bar, right, I know the saturation pressure is going to be much less than 1 bar. Okay, but if I'm thinking about a case like this, right, we could say my pointing correction is negligible. If I'm at low pressures, so I can assume my vapor phase, right, because this is going to correspond to two-phase system, pure water at vapor-liquid coexistence. So if I'm at low pressures, right, and saturation pressure is going to be less than 1 bar, right, because it's water at vapor-liquid coexistence. If I can assume my vapor phase is an ideal gas, right, then this is just equal to 1. And so to a first-order approximation, then, the Fugacity of my pure component state at T and P is just equal to my saturation pressure. And when it comes to my saturation pressure, I could compute that using, say, Antoine equation or look it up if I have tabulated data. Right, and so by expanding this, right, this is going to give us this mechanism by which we can, systematically make approximations to be able to actually perform calculations. Okay, and then the second part that'll come in when we talk about Rayleigh law, but since I have it here, is the other key is when I perform these expansions of fugacities, right, we get mole fractions in them. Right, it can't be understated how important that is. I'm a chemical engineer. The problems I'm interested in are typically separation processes. So if I'm designing the distillation column, what I want to know is the mole fraction, all right, coming out the top of my column and at the bottom of my column. All right, I want to know the mole fraction coming out of the condensing unit at the top and the reboiler at the bottom. Right, I want to know compositions. And so when we expand our fugacities, right, as we get a preview here, we end up getting expressions that are explicit in composition, right? They're explicit in the what we're actually trying to solve for, which is going to be the second kind of benefit or such. All right, so that's the fugacity of component I in a pure component state. So then the fugacity of component I in my ideal solution is just mole fraction times that, and so it's going to be xi times phi sat at T and P sat times pi sat at T times the exponential of my Poynting correction. Okay. Boom. Okay, that would actually be, pi sat. You could think of it as, at T as well. But, this is mole fraction component I. That's the fugacity of pure component I at the same T, but pressure corresponding to saturation pressure. That's its saturation pressure and my Poynting correction. So I'm going to stop this video here, because then what we'll do is I'll pop up next and we'll use this in terms of deriving Rayleigh law. Okay, but yeah, hope that helps. And again, just want to remind you of the similarities, and then also, last comment is we have ideal solutions here. Remember, pure component solution is an ideal solution, right? A pure component solution is an ideal solution because all of those interactions are exactly the same. The molecules are all the same size. Okay, we'll see you in the next video.